Morning, everyone. So yesterday we started looking at alkenes. Alkenes have a characteristic double bond between carbons. A double bond is made out of one sigma bond and one pi bond. That is an electron-rich region. That is going to seek out places that have positive density, so that in itself is a nucleophile. And we end up seeing how we can add an electrophile, add up something that sort of bonds to the negative density. In addition, reaction takes two things and actually combines them just into one thing. As I mentioned here, just to try to keep these reactions clear, it's always a good idea to start off your practice here. See if you can just do the mind map. Right. So far, we've just been sort of building on our organic reactions here. Let's start off with what we know, which is alkanes. What are some reactions that an alkane does? Right. Well, an alkane reaction here, it's going to burn. Let's say it burns. What we need here is going to be oxygen to burn. I'm going to put CP just for combustion products. Okay. So it could be complete combustion to CO2. If it's incomplete combustion, carbon monoxide and some carbons. Okay. Alkenes can also, in the presence of UV light, right, you need that UV for the initiation step here, reacting with Cl2 and Br2, it can actually end up forming a halogenoalkane or a alkyl halide. Either name is fine. Right. We'll see reactions of alkyl halides later on. But aside from those two, which need such high energy requirements here, alkenes pretty much kept to themselves. We found alkenes were a lot more interesting. So alkenes here, we can actually undergo a process here. Alkenes can be converted into alkenes. So let's think about that for a second here. An alkene here has a carbon double bond. What do I need to add across the double bond so that I end up having just hydrocarbon? In this process here, I would refer to that reaction here as hydrogenation, not hydration. Hydrogenation, I am hydrogenating something, I'm adding hydrogen. So that means hydrogen is definitely the thing that I'm adding. This one here, the reacting conditions that we needed a heterogeneous catalyst of nickel. Sometimes they use palladium, platinum, that works as fine. This one is the one that slightly needed a hotter temperature, so let's make it 150 degrees, okay? If it's 160, still works. 140 probably still works, but just needs to be slightly hotter than room temperature. So that's one other thing I can sort of add to this diagram. Can I convert an alkene over to a halogenoalkane? A halogenoalkane would have all carbons single bonded. You may have some X's, some other halogen groups on the side here. Well, what am I adding across the double bond so that I end up with an X group? Well, you should be able to tell me here, I actually want to add an HX, right? Where the X here could be chloro, bromo, iodo, right? So those ones there, this totally occurs just at room temperature, so I'm just going to put RT for short, as opposed to the 150 degrees from earlier. Right? It's possible that you could add a halogen by itself, a diatomic across it. This one here I'm going to give you a new name. Also occurs at room temperature, but this one here I'm going to actually add an X2. Right? So again, it could be your fluoro, chloro, bromo, iodo. This one here, new name. Well, we're just sort of summarizing what we would have. If I have added, let's say, an F and an F across there, it would be a alkane with two halogens, so a dihalogenoalkane. Right? So all I'm doing is I'm adding different electrophiles across the double bond. The double bond is converting itself into a single bond no matter what I'm doing. I didn't do this reaction with you, but being a so hydrocarbon-rich environment here, I would imagine alkenes would also burn. So let's add O2. That's why I can just go to combustion products. If I burn things later on that have nitrogens, I might get some NO2s, sulfurs with SO2, things like that. That's why I'm just saying CP for general there. So that reaction can happen. One of the most important reactions that we learned from yesterday was in an equilibrium reaction. This one here actually required concentrated sulfuric acid, or any acid for that matter, but concentrated sulfuric acid, we actually were able to add, the chemical was actually adding a water across. And remember, for water, what ends up happening here is we would have C like this. Although the acid is the thing that adds first, we end up getting the H from water and the OH acid the other side. What family have we just made? Well, the OH I know is the hydroxy family. I know it's the alcohol family. I have actually ended up forming an alcohol by doing so. So we can convert an alkene to an alcohol reversibly with concentrated sulfuric acid by adding water. And just like again, lots of carbons and oxygens, things like that. One of the reactions, we're going to study alcohols a lot more in today's lesson here, and alcohols will also burn, so plus O2. So you already start seeing the mind map is starting to get a little bit larger. I'd encourage you every day before you start studying, just sketch out the mind map for yourself, see if you can memorize some of these reacting conditions for yourself, and therefore you can get more familiar with this process. Okay. So I'm going to give you sort of two side questions here. Since we did talk about the equation in forming water, I want you to just state the products. So let's say part A. State the product for the reaction. Let's do it between propene and water. They're going to give you hints that, oh, this one here requires concentrated sulfuric acid. That is important because if I don't have that catalyzing the reaction won't occur. If they just say state the product, you just give me the answer. So let's just try propene. Well, it is a double bond between carbons. Let's try the double bond. Normally, I would need a number for where the double bond is, but it turns out if I put it here, it's one propene. If I put it on the other side, I count it the other way, it's also one protein. I'm going to add water across it. So water, I'm thinking of an HOH like this. It's the double bond. That's the reactive portion, right? That's the electron-rich region. The water here is a polar compound. Ultimately, what's going to happen here is it's an asymmetric electrophile that I'm going to add. So we're going to need to do Markovnikov's rule. So we have a carbon having two hydrogens, and this carbon here only has one hydrogen. Markovnikov's rule says he who has gets more. The one that's already bonded to more hydrogens ends up getting extra hydrogen. So if I'm going to add an HOH, I had the possibilities of either going OH and H like this, or I could have the possibility H and OH. Those would be different compounds. The hydroxy would be on different positions. This one here would be my major product because my H ends up on the one that's more highly substituted. The double bond has now become a single bond. So if I'm just sort of writing that reaction out there, again, reversibly here, we're going to end up getting, oh, the carbon on the end here actually ended up getting yet another hydrogen. He who already has hydrogen gets more hydrogen. How unfair is that? And we end up getting OH. In the next question that I'm going to ask you, we can show the mechanism and explain why that was. But there we go. They might ask you to name it here. This one here, 2-propanol or propane 2O. Either is fine. Okay. So sort of in getting us to think about why this was the major product, why does Markovnikov's rule work? Why did I add the hydrogen to the one that was already more highly substituted? Let's just practice one more on the side here. What I want you to do is I want you to show the mechanism to explain the major product. If I have something that's symmetrical, right, maybe I can't identify which one was major product, but I'm going to give you a situation where we can. Let's try a situation 2-methyl-butene. And I'm going to add an HBr across it. Okay. First thing you want to do is you want to think about reacting conditions here. We have an alkene, and I'm adding an alkyl halide. That would just occur at room temperature. No need for a catalyst. No need for slightly hotter than room temperature. That was needed for hydrogen. So as always, let's just start off drawing. So butene here. But is 4. At position 2, a double bond starts. And now in position 2, we also have a methyl group. This one here is an asymmetric alkene because I can tell methyl group on one side, but the hydrogen group on the other side here. This one here by itself would have cis-trans isomerism or would have EZ isomerism, actually because of the methyl group on both sides. You can't actually tell, but by the time we actually add the hydrogen halide across, it becomes a single bond anyways. I don't need to worry about the isomerism. So let's try it out here. Let's do the mechanism. So we have an HBr. And HBr here is a polar compound. So it always has a slight imbalance that bromine is actually kind of negative, whereas the hydrogen side is kind of positive. We call the HBr the electrophile. The electrophile eventually gets added to the double bond. That's why we call this electrophilic addition. But remember, when we draw arrows, we always draw arrows for what the electrons themselves are doing. So we're going to take the electron-rich environment of the double bond, the sigma bond and the pi bond specifically. Because there's so much negative density, we're going to do a double-headed arrow. That's actually going to form a new bond with the hydrogen. the bond here, which was made out of 2 electrons itself, actually jumps over to the bromine. Because this was an asymmetric hydrocarbon, there's 2 possibilities that can happen out of this. So I'm just going to sketch up both possibilities. So the double bond has already become a single bond. One possibility has the hydrogen added across here, so my carbocation is on the right. Or I have that same molecule, methyl hydrogen, or my hydrogen, it is going to add across the double bond in either position, or the hydrogen adds across here, and we have the positive here. So before the bromide can actually attack and rejoin and actually synthesize to form the same adduct, the same addition process, we need to figure out, well, which one is the major. Make a note to yourself here. The major product goes through the more stable carbocation. And we had seen from yesterday here, based on the positive inductive effect here, the stability of carbocation, tertiary carbocations are the most stable, then secondary, then primary. Basically, any alkyl groups, any carbon groups can donate some of their electron density to the carbocation to help stabilize it. So if the hydrogen added to the left-hand side, we have a secondary carbocation, not too bad. The carbons on either side can donate some of their electron density, can help to spread out some of their positive. If I do the other side, though, if the positive ends up on the left, we end up getting a tertiary carbocation. Well, this one here, tertiary, is actually going to be more stable. So that means it's more likely the hydrogen is going to add to the right-hand side, forming the tertiary carbocation long enough for the bromide to end up attacking the carbon on this side. And therefore, we end up getting 1, 2, 3, 4. Still methyl hydrogen. We've actually added the hydrogen on this far side here, and we end up adding the bromide. Okay. We can name our product here. This one here is still a butane. I now have a bromo and a methyl, so maybe 2 bromo, 2 methyl butane. This one here, you could ask yourself, does this have RRS isomers? For RRS isomers, we need to have a chiral carbon. We need to have carbons that are bonded to 4 neighbors. This carbon has CH3. Well, it's same neighbor, 2 hydrogens. This one here is CH3. The only possibility may have been this carbon in the middle, but I also notice it's holding a methyl group and another methyl group. So because it isn't 4 different groups, everything is asymmetric. This is not going to be optically active. Okay? I wouldn't be surprised if you actually didn't form any of this, because it's the more stable carbocation that ends up reacting. Okay. Let's check if Markovnikov's rule predicted that. So we have a double bond. One carbon is holding no hydrogens. One carbon is holding 1 hydrogen. If I add an asymmetric halide, if I add the hydrogen, where should the hydrogen go? Let's add the hydrogen to the right-hand side, because therefore it ends up putting the carbocation on the other side. The other one that has less hydrogens is going to be the more stable carbocation. Then bromide can attack that position. So that's an explanation. Markovnikov's is just a nice shortcut for that. Okay. So way more interesting than just alkene, but we just added to that mind map there. Okay. Today what I want to do is I just want to quickly finish off with the alkenes. Turns out alkenes can form what are called polymers, and then we're going to work our way, once we've added water in the presence of sulfuric acid, this one here can actually end up forming alcohols, and we'll see a few nice reactions for that there. So alkene, so new reaction, we haven't seen this yet. An alkene can also react to form a polymer. A polymer is a long chain of monomers. Monomers are the single units that I basically glue one after the other. And basically what's ending up happening is it's going to actually repeat very, very many times. I'm just going to say to the nth time. So for example here, we have our monomer. Our monomer right now here is ethene. So 2 carbon, double bond. Well, again, being an electron-rich region, I know this compound here is nonpolar. Based on the electron switching and swashing, the electrons may happen to be switched over to one side. I have a temporary partial positive, a temporary partial negative. Well, the electrons here are going to attack the positive end. What about the electrons here? These electrons here are going to attack the positive end here, and they're going to attack again and again and again. Again, this is the single repeating unit that we're going to do. I know, just sort of based on my predictions, a double bond becomes a single bond. So just for that monomer unit here, that's become a single bond. The substituents that I already had are still going to be attached. And all that's going to happen here is, now that I've actually attacked the next carbon over, I've now formed a longer carbon, right? I would have a butane here, but in this case, because it repeats what I say n times, right? It just repeats over and over again. This is going to attack the next carbon along, and what we're going to end up talking. Typically, they make nylons and plastics out of this here. We're probably talking about maybe thousands of carbons long. It just keeps repeating, it keeps attacking over and over again, and this has now been referred to as a polymer. Okay, so it is an addition reaction where an alkene attacks another alkene again and again. So these are actually what, as mentioned, some plastics are made out of. Plastics are usually graded. They have a certain number to them here. Depending on what the grade is, you might see for a particular plastic, HDPE, used for Tupperware, pipes, and hard plastic. That's high density polyethylene. Whereas low density polyethylene here, those six-pack the rings holding the cans together here. It's a more flexible plastic here. It really just depends on what else is actually attached to the polymer group. Okay, so let's just make some predictions here. This time we have a slightly different monomer, right? The monomer earlier was just carbon with all hydrogens. Now I've actually added Cl. Usually things that have Cl will be referred to as vinyl. So if you hear PVC, a very common building material for insulation, for pipes, things like that, they would typically contain chlorines in them. That's graded at a 3 there. That number, plastic is 3. But again, what ends up happening here is this monomer here ends up attacking the next one, attacking the next one, attacking the next one. They can ask you, can you draw for me? Well, what's the remaining? Again, double bond has become a single bond. I just draw my attachments. This time my monomer had 1 chlorine. As I attach to the next monomer here, also a single bond here, but every time I'm going to have a chlorine. Slightly harder question is them asking you, okay, here's a monomer. Well, what was the monomer that it was formed from? What was the basic that it was formed from? You just look for a repeating pattern here. Well, that one there would be our monomer. Okay, so this one here is polyvinyl chloride, right? It's N times of this alkene. Again, graded at a plastic of 3. Let's do a slightly different one here. This is polypropene, which should actually be polypropylene here. This one here, again, as our monomer here, our double bond has now become a single bond here. So far, one carbon always has 2 hydrogen. The other one, instead of being vinyl and having a chlorine, we actually end up having a methyl group and a hydrogen. So that's a monomer. Let's imagine repeating that again and again and again, and we're going to end up getting a polymer of this. So I'm just color coding it so you can see the monomer unit. Okay. And just remember, a double bond became a single bond. I basically still have my 4 attachments, but this one here is repeated N times. It's repeated many, many times. So that one is polypropene, used for a lot of plastic bottles, clear bags, and packaging. Unfortunately, because this is so saturated here, it's very hard to break down plastics. But for everyday use here, a plastic bag might be more convenient than, say, like a paper bag. Okay, totally possible that these chains here can even be longer. I can have like a longer substituent here, but basically that substituent would just repeat over and over again. Okay. So some sample questions out of here is, can you draw and name the polymer? Basically, you draw this alkene and you repeat it over and over again. Or if I give you this alkene here, see if you can get a repeating pattern. Well, that's the monomer unit. It would have been C double bond C, and then having this hydrogen bromide and then the methyl and the chloride. So not too hard, hopefully. Okay. That finishes off our study for alkenes. I want to finish off today's lesson in taking a look at an alcohol family. More interesting reactions, but fortunately for us, we don't really need to know the mechanism for this part. Okay, so let's just switch over. Your next page over should be an alcohol. An alcohol here should have the functional group. It has a very specific grouping here. It has a specific grouping of OH, and that OH is actually O, like single bond to O and then single bond to the H. Okay, so that one there is my alcohol functionality. I want to know what sort of reactions does this one do. So notice the formula for alcohol are written. Technically, we are still all single bonded. This one here is written so that the OH is sort of by itself. CX, HY, and then I still have an OH. I could have condensed the hydrogens all together, but I really want to point out, no, the OH is actually together. That gives me some polarity. That gives me some specific behavior. Okay. So it clearly shows the hydroxy group. That's the name of the OH group. Sometimes that was named as a prefix, as a branch. The hydroxy was an OH. that is the very same OH that a base has, but we already talked about it before. If I have NaOH, why is this a base? Not only do you need to have hydroxide, you need to be able to release the hydroxide in water as an ionic compound, no problem. If I have methanol instead, unfortunately the methanol is actually covalently bonded. The OH here is exactly the same as the OH earlier, but being a covalent compound, dollar for dollar, covalent compound is stronger. Water cannot separate this. This is now referred to as the alcohol family. This would be molecular in solution. It's an individual grouping, not even charged, not even dissociated. This way of showing, emphasizing the OH group keeps us apart from another family here called an aldehyde. Remember, when we practice the naming of these families, you do need to name the different functionalities and draw the groups. An aldehyde functionality here would be something like CHO. Also has an OH functionality here. Even though I shorthand the CHO group for the aldehyde group, I know the H can't be in the middle. The CHO group is actually C11O, but it is terminal. That's why we didn't need to have numbers for this carbon here. Okay. I already mentioned on our mind map, even the alcohols that we produced, take an alkene, reacted with water in the presence of sulfuric acid. These ones here can combust, so that's the first easy reaction. Let's take propanol, C5H11OH. Let's react with oxygen. You always assume complete combustion. So complete combustion, we have excess oxygen around, we fully oxidize to form CO2 and water, and then it's just a practice of balancing here. So I have 5 carbons, let's try 5 there. I have 12 hydrogens altogether, I need a 6. 5 times 2 make 10, plus 6 here is 18. 10 plus 16. That would have been nice for this, but unfortunately I have 1 oxygen already. So sure, that leaves me with a fraction, so be it. That's fine. This will be the heat of combustion for burning 1 mole of pentanol. Okay. Just like we saw for carbocations, for alkenes, there are primary, secondary, and tertiary designations. This one, you can shorthand it. It's sort of the number of carbons attached. But remember, when we actually define this here, let's say methane here. Methane actually doesn't have, let's actually put methanol. Methanol here actually doesn't have any carbons. If you just follow this rule of number of carbons attached, you'd say, well, it's 0 degree. Well, this one here, we still say it's primary, right? This one here, you could have even 1 carbon involved, you're still primary, but by defining it earlier, we can sort of avoid that. Usually you can tell just based on how many carbons are attached. Okay. So let's try this here. Primary, secondary, and tertiary alcohols will behave differently. The next reaction that we're going to talk about is the oxidation of alcohol. So what we're going to use is an oxidizing agent. There are 2 common oxidizing agents we use in organic chemistry. The one that we're going to mainly use here is potassium dichromate, K2Cr2O7. The other one is potassium permanganate. The only problem here is this potassium permanganate is usually too strong. So KMnO4 can also be used as an oxidizing agent. It itself helps something oxidize. In the process it gets reduced, but usually too strong and ends up oxidizing other functionalities, other functional groups before the OH group that I want to oxidize. Okay, so that's why we typically use something a little bit more easy to work with here. The dichromate here, it's actually the Cr2O7 in acidified conditions here. They show you, notice, hey, wait, these are reductions. Why am I calling? Well, they were oxidizing agents. Remember, by definition from a redox chapter, hopefully you still remember this here. Oxidizing agent, it helps others oxidize. And we're actually just going to use plus O for some oxidizing agent, not oxygen, right? But it helps others oxidize. Itself usually gets reduced. And reduced here, Leo the line says GR is a gain of electrons. We expect the electrons to be on the left-hand side. So they actually demonstrated both of them for you here. The reason why these are so common here is they actually come with corresponding color change. If you manage to use KMnO4, we're taking manganese from the +7 state down to the +2 state. The +7 state here is a really deep purple color. So you can actually tell, be it a titration or whatever, if the permanganate is still there, if it's staying purple. Mn2 plus is actually colorless. For the dichromate, also very interesting. Dichromate was actually used for a lot of breathalyzer tests. This is chromium in the +6 state. The oxidation state has to be signed first in the number. In this case here, it actually starts off, chromium +6 is actually orange. You blow into a breathalyzer, the alcohol here is showing an orange coloration with this indicator. Depending on how much alcohol is in the breath, depending on how much actually gets oxidized by the dichromate, it converts some of the dichromate over to the Cr +3 state, and the +3 state is actually a nice green color. And then your breathalyzer test here would just test, well, how much orange is there, how much green is there, have you shifted it too far over, is there too much alcohol in the breath? Okay, so we are looking mainly, yes, in some sense, even a combustion is oxidation, but that one, oh, just simple, burns to CO2 and water. We're looking at some more interesting, what if oxidation is happening a little bit more gently with the dichromate versus a potassium dichromate? So we're going to start off with the least reactive. Tertiary alcohol here, again, it's the carbon. Oh, it's attached to 3 other carbons, right? So we can make here 3 other carbons attached to the carbon with the functional group. Right. Remember, it's the functional group that actually gives it behavior. I want to right away look at the carbon that's holding the functional group here. So that one there is tertiary. You can see better for the other ones. Well, the carbon that's holding the functional group here, this is secondary. 2 other carbon neighbors. This carbon here is primary, right? Notice that's not an inductive effect. I'm not saying it donates electron density. I'm just saying how many you're attached to. In this case here, our conditions for oxidation, again, you can just say +O. Usually it needs a little bit of heat treatment as well. We're going to put on the conditions. It needs to be acidified dichromate. Dichromate here is our oxidizing agent before. We needed acidic conditions, right, for this reaction, or else we would just skip this one here on the redox table and keep going. Usually what we need to do is we need a little bit of heat, right? A little bit of heat is not a problem, right? It just sort of gets the particles moving around a little bit faster, gets them potentially colliding, better energy, better geometry here. A little bit of heat. We can even do what's referred to as a reflux in this process. I'll talk about what this means in a second here. But it turns out because the carbon is already so highly substituted here, I can't oxidize this group here. I would end up needing to break this molecule here. This one here actually has no reaction. Okay. We need to break the structure to oxidize, which doesn't happen because we have other carbon groupings. So what I mean by this breaking structure here, we'll see it better with our secondary alcohol here. Again, I could say the exact same ingredients, H+, CrO4, and whatever, just getting you used to different ways of writing it. Sometimes you just say in words, I'm going to use acidified dichromate. Well, acidified dichromate has H+, has the dichromate, that's an oxidizing agent, that's fine. And then what we're going to do is we're going to, again, that triangle, sorry, I didn't write that down, that triangle actually refers to heat. Just a little bit of heat treatment. We're going to talk about reflux very shortly here. We're going to reflux this process here. This one here, we can actually, if it's a secondary alcohol, we can oxidize it. What would this compound look like if it has sort of more oxygen importance here? You can actually think of an oxidation. I'm going to give you the answer first. So this is actually going to be, it actually has oxidized. We have broken a little bit of the structure. We haven't broken a carbon-carbon. None of the parent has broken, but we've just managed to break off a CH bond, and we've managed to oxidize this O into the double bond O state there. Okay. In this case here, we end up forming a ketone, right? Like an aldehyde is a carbonyl group, it is a C double bond O group, but this group here is actually somewhere mid-chain, is not at the end. So carbonyl group at the end, and basically this one here is a little bit more oxidized than before. You don't need to know the mechanism of this here. You can just memorize, okay, if I take the OH, that's the most reduced form. That's why I wanted to write down here. We're thinking, so what is an oxidation? An oxidation, usually, for the longest time, they thought it had to involve oxygen. Oxidation can be thought of. Oxidation is, you can think of as gaining oxygen, right? That would cause your oxidation state to go up. Or usually, if I replace the oxygens with hydrogens, I say that's a reduction process. In this case, if I want oxidation, or you can think of it as a loss of hydrogen. If I sort of lose hydrogens, I lost that CH, I lost that O attached to the H there as well, that would be an oxidation. You can check the oxidation state, and lo and behold, yes, it does go up. Okay. Primary alcohols are the most interesting. Before we come back and take a look at this sort of what is a reflux, we're actually going to do this in 2 steps. For a primary alcohol, it's only attached to one other carbon neighbor. What we can do is we can actually oxidize it twice. So again, most generically here, they can say add some oxidizing agent. I can say dichromate, I can say even potassium permanganate if it doesn't interfere with other functional groups. You need a little bit of heat treatment. But this one here actually takes place in 2 different steps. The first sort of more oxidized form here, like earlier, we want to break off some of these H's. But before all the H's break off, we end up forming a temporary sort of ingredient here. We end up getting our C. That group was beside here. We have carbon. We get that C11O, but I still might have my hydrogen. This one here would be my CHO group from earlier, and this CHO group is actually an aldehyde. So for a primary alcohol, right? Oh, big deal, right? Secondary alcohol formed a ketone. Primary alcohol ends up forming an aldehyde. Turns out an aldehyde, which is the CHO functionality, that's not even the fully oxidized state. I can keep heating it and keep oxidizing, keep having that oxidizing agent in. This one here would actually typically need reflux. Again, I'm going to tell you what reflux means in a second here. And I can further oxidize it to end up forming CH3. That's still on the end. Even adding more oxygens here, we actually have converted this one here into a carboxylic acid. So again, a really nice reaction for you. We took an alcohol. We got an alcohol from take an alkene, add on a water in the presence of sulfuric acid. With this alcohol, if I heated it just a little bit, usually this first process here, we would use a distillation. We can get aldehydes, or if I fully oxidize it, I even give it even more oxygens. I don't need to know the mechanism for this, but fully oxidized, I end up getting that COOH functionality, and that's actually our carboxyl functionality. It is acidic, so it is going to release hydrogens in water. So I want you to know here, the oxidation of a primary alcohol results in 2 potential products. This is not major minor. This is more so how far have I oxidized it. One of them is potentially an aldehyde. The other is potentially a carboxylic acid. It just depends on the extent. It depends on how far you push this oxidation onwards. The aldehyde always forms first, and then further oxidation ends up producing the carboxylic acid. So let's say I want to actually separate it at the aldehyde state. Okay, so to make the aldehyde, to collect just this middle product here, let's take this ingredient here. So I have ethanol. We want this one here to oxidize, right? So it could be acidified dichromate, it could be potassium permanganate here. Again, typically I'm going to use that triangle. That triangle here means heat. Again, the emphasis here is I'm actually going to distill it, and I'm going to draw you these processes here. This one here would manage to just collect off the CH3, the aldehyde family before it actually further oxidizes. So let's just compare these here. We have 3 potential things here. I started off with my alcohol. So I started off with ethanol, right? That's molecule number 1. My aldehyde is slightly more oxidized. I've lost the hydrogen. I've lost this hydrogen here. I managed to break a little bit of the structure, but I'm not breaking a C to C bond. That's my aldehyde. And if this fully goes completely, it's going to end up forming a carboxylic acid. What physical property would these ones here have different? This first one here is an alcohol. Second one here is an aldehyde. And the third one here is a carboxylic acid. Okay. So now they have roughly the same number of carbons, so London force could be similar. What I want to check inside the compound is whether it's polar or nonpolar. Okay. What you do find here is alcohols are polar. They have H tug-of-war against a really electronegative element here. This one here has hydrogen bonding. So I would expect this one here has very, very high boiling point, high melting point. Similarly with the carboxylic acid, not only does it have the hydrogen bonding from the OH, it also has a dipole-dipole force from the C-double-bond-O. This one here I'd expect to have the highest boiling point, slightly higher than earlier, because it does have H bonding and it has dipole-dipole. Remember, when you talk about intermolecular forces, don't tell me how many hydrogen bonds. You just tell me it has access to hydrogen bonding. So this one has the even highest. An aldehyde also is a polar compound, but it doesn't have H, losing that badly to an oxygen. So this one here only has dipole-dipole. So this one here would be a more medium boiling point. So what we can do here is we can actually control how far the reaction goes. They're talking about this as an extent of reaction, either with this word here, distillation, or with this word here, reflux. So I'm just going to show you a picture of what this looks like on the back side. An organic chemist here can control which product is actually formed. What's shown here is actually a distillation setup on the left. You might remember this one here from the separation techniques we did back in grade 11, but it's been a long time. So that's a distillation. This one here is called a reflux. Essentially, both of them involve using a condenser. So let's imagine this is our primary alcohol in both cases, primary alcohol. This is the one that is fully reduced. It isn't oxidized yet, okay? You might end up slowly adding alcohol inwards, but let's just say that all the alcohol is here. What we're going to do is we're going to put this under a heat source, okay? Under the heat source, aldehydes have the lowest boiling point compared to even the alcohol I started with or the carboxylic acid, and the conclusion there is the aldehyde, it boils first. So imagine starting here with my primary alcohol here. You add in the acidified dichromate, you add in some oxidizing agent. Slowly it's going to convert alcohol over to aldehyde. As you have aldehyde, the aldehyde is going to be the first thing that boils off. The other ones have hydrogen bonding, they're not going to boil as easy. As this aldehyde gas here leaves the container, I don't let it just go into an open system. I actually shunt it down this side here. And what I do is I run cold water around the outside. This guy here is called the condenser. The condenser here, the cold water surrounding condenses the aldehyde gas back into liquid, right, to make it easier to store. So I purposely made it a gas so the aldehyde can escape from the alcohol, can escape from the carboxylic acid. As I just sort of shunt it down this side here, the hot gas runs into a really cool environment and ends up forming little droplets of condensation. Those droplets are sort of running off into the other container, and there I've collected the aldehyde. This is called the distillation setup. Usually when we purify crude oil, that was fractional distillation. When we purify ethanol for beverages, that's also through a distillation. It's one way of sort of treating this alcohol. What a reflux does here is essentially the same. We're going to take our primary alcohol. We're going to throw in our oxidizing agent. Could be potassium dichromate, could be KMNO4, no problem. This time, it's nowhere near as complicated. I don't have to keep adding alcohol. This time, I'm going to still have my condenser. And this one is just more so, I'm just going to heat it. Just don't even watch it anymore. What's going to happen is the alcohol is going to start converting aldehyde. Well, it's already so hot. Yeah, the aldehyde runs up. Well, it can't escape really far. It condenses in liquid and it drops back in. The aldehyde keeps getting oxidized, ends up forming a carboxylic acid. Even the carboxylic acid and the alcohol will start boiling off as well. But because all this hot gas, first thing is nothing is separated, all this hot gas runs into an environment that's actually condensing. It condenses, it keeps the gas inside, and it allows it to boil off for longer. We're going to call that process a reflux process. Okay? So just keep in mind here, because of this nice feature, an aldehyde actually has the lowest boiling point, even compared to the starting ingredient and the carboxylic acid, the fully oxidized one. If I do a distillation, if I end up collecting it in a side chamber, I can end up collecting this medium product. Whereas if I just reflux, I just condense it. I basically heat it for long periods of time. This one here will end up making a carboxylic acid to collect carboxylic acid. All right. So try it for yourself. See if you can add some of these reactions here to that mind map. I'll do it with you in tomorrow's lesson. But therefore, we're starting to get more interesting reactions. Okay. Let me know if you have any questions. Thanks, guys.